good morning, and thank you for being here so early in the morning. My name is Ana-Equirectangular. I'm a PhD student at ETH Zurich, and today I will present my publication, Rectangular 360-degree image dataset for detecting reusable components, which was developed together with my dear colleague Jens Hunhevicz, with Professor Karsten Menzel from TU Dresden and Catherine Wolf from ETH. So climate change is one of the biggest challenges on the global scale, and the construction industry is both one of the biggest resource consumers and waste producers on a global scale. Transitioning from a linear economy to a circular economy is essential for mitigating the environmental impacts from the construction industry, and reusing components is one of the key strategies. Reuse in the construction industry refers to the non-destructive dismantling of whole components to reuse them in a new project with the same function. To enable circular strategies, and specifically to enable the component reuse, we need precise information on the existing composition of the existing building stock. However, in practice, we often lack reliable as-built data. And this is further aggravated because reuse or circular strategies are often not planned ahead but decided last minute, so that the time frame of inventorizing a building, recovering the materials, and reintroducing them into the market is very short before the demolition. So all of these challenges enhance the need for a holistic approach that delivers fast, easy to apply and digital solutions for building stock inventory. In our work, we envisioned an application of 360-degree images for documenting in situ buildings in the end-of-life stage and using machine learning for detecting reusable building components. Why would we use 360-degree images? We noticed that they are increasingly being used for building documentations because they are easy to apply, they provide a comprehensive view, and they reduce overall documentation efforts. However, a deployed computer vision model is only the result of several prior steps. The model needs to be trained and tested on a suitable data set. However, when we first started with our research, we noticed that there is no publicly available panoramic data set that would fit the requirements of circular strategies. That is why the scope of our work has been on the generation of a suitable data set and on the validation of the overall approach. What is a suitable data set? So suitability of a data set means that it fits the requirements of relevance and also the quality for the envisioned application. The relevance of training data refers to the extent in which the training data aligns with the data that is expected in the production stage, while the data set quality refers to all the aspects that influence the generalization capabilities of a model to unseen data. So the relevancy of the data set for end-of-life scenarios was ensured in the case study selection. In 2022, 85% of all residential and non-residential buildings demolished in Germany were constructed before 1986. So keeping that in mind, for our case study, we selected 5 publicly accessible buildings on the campus of the Dresden University of Technology, according to their age, their architecture, and also their use stage. We have buildings in this case study that are partially gutted and not used or partially used. We have some of them that are completely empty for renovation, and some are still in use, which quite well reflects the end-of-life stages of a building. So while the relevance of the data, was ensured in the case study selection, the quality of the data set is addressed in the data set generation. The data was generated using a 360-degree camera helmet, and the data was generated on different days and times of the day to ensure variance in the lighting and shading conditions. And additionally, the images were not taken with a fixed object distance, which results in a variance in the object's appearance, in the scale, and the occlusion of the objects. So once the data is generated, the most important part is to define what should be detected and in what granularity we want to differentiate between the different building components. So the EU policy fails to provide regulations or prerequisites of what is reusable without prior destructive testing. That is why we conducted a broad field study of the most common reused material markets and also practice guidelines to identify components that we can deem as reusable by a default. In this field study, we identified 5 building component categories, namely windows, doors, sanitary lamps, and radiators. They were chosen because they are considered reusable without prior destructive testing. We have large intra-class variations, meaning that we have very different types of doors, for example, and also they were captured in large numbers in our case study. So after we know what to detect, we have to see how to detect. And conventional object detection data sets usually have very broad categories, so they only differentiate according to the component type. However, for the application that we envision, we need to meet two requirements. We want the output of the model to be compatible with building process planning, so we have to stick to some extent to existing standards. And on the other hand, we also want to provide a foundation for reuse planification. That is why in the annotation process, the first, we labeled the components according to the structure of the German national standard DIN 276, and then further differentiated according to the function, the material, and the design. The annotation process resulted in 136 different object types, so object classes in computer vision, and after the split into the training, the validation, and the test set, we had a finalized data set of around 2,700 annotated images and more than 12,000 bounding boxes. So once generated, we wanted to validate the overall approach. And if we look at 360-degree images, dealing with them presents very unique challenges compared to two-dimensional regular RGB images, which are namely because of the distortions, but also because objects of the same class can appear very differently depending on the distance on the camera perspective, and also we have large variations in shape and color. So there are generally two approaches on how to deal with 360-degree images in computer vision. And the first one, we take the two-dimensional but distorted projection of the sphere onto a plane called the Equirectangular projection. And the second one, we circumvent the distortions by creating crops in the sphere that are normal to the camera viewpoint so that we don't have distortions in the object's appearance. For our initial validation, we chose the first approach and used the state-of-the-art object detection model YOLO version 8. Finally, in the test run, the test run was performed on the test subset of around 120 images and around 1,000 instances. We can see that in the test metrics that in this very first run, this initial validation, a large proportion of components could already be effectively detected, but we can also see that the mean average position in an intersection of a union is not very high. This mean average position, as the name says, is average across all the classes. So if we want to draw conclusions on how to improve the data set, we need to have a closer look at specific classes. So in the diagonal of the confusion matrix, we can say that most classes are confidently predicted. In fact, in the test run, we had over 60% of the component types detected with higher precision than the mean average position, and even 30% had a higher precision than 90%. But what we also have to see is that we have a lot of outliers, and specifically these here in the bottom, we can see that some of them are very confidently detected, but then classified as the wrong class with a high confidence. So if we want to, in future work, we need to address these classes specifically by adding high quality data or more data so that the model can extract the features to differentiate between these classes. Since the scope of this work has not been to train the best model, but on validating the initial approach, I would like to conclude with the contributions and the limitations. So the contribution of this work has been that we validated an approach on how to generate in situ images for end-of-life scenarios. We delivered a fully labeled data set. And finally, we present a workflow that is extendable to more component categories. And I would like to conclude with the limitations of this work that showcase where our future work is heading. We group them into three categories, so regarding the case study, the annotations, and the model. Regarding the case study, future work needs to address the diversity of the data set. We need to prove the scalability of the approach to large and more diverse data sets. In the annotation process, we can see that we have limitations because of the limited amount of component categories, and also it was quite time-consuming, so it might be worth considering broadening these categories and then using cluster algorithms to further differentiate. And finally, we need to compare this initial model to other models and need to assess the robustness and reliability. Addressing these limitations can hopefully help us progress towards an automated building stock characterization in a more circular ISC sector. Thank you.